everyone, and welcome to another video on high-performance computing for Ansys Mechanical. The main focus of today's video is to share some details that users should consider when deciding what type of CPU to purchase when trying to optimize performance. Now, my name is Jeff Beisheim, and I'm a Senior Principal R&D Engineer at Ansys, and I'm joined today by Herbert Gutler, who is the owner and founder of MicroConsult. Ansys has been collaborating with MicroConsult for over 15 years now on the specific topic of HPC for the Ansys Mechanical product. Ansys Mechanical APDL currently only supports x86 processors, and the two suppliers of these x86 processors are Intel and AMD. In one of our earlier videos, we discussed that Ansys Mechanical APDL is built using the Intel compilers, the Intel math libraries, and the Intel MPI libraries, which is often a compelling reason about why Ansys Mechanical APDL runs so well on Intel processors. However, AMD processors have made significant advancements in the last few years, particularly with respect to their EPYC line of processors that are targeted for workstations, servers, data centers, and these improvements are not to be ignored.
Okay. So, if you look at that slide, at the year 2003, AMD introduces the Opteron processor. This comes with some fun memories for us because actually an Opteron server was the first real number crunching server that we purchased as MicroConsult. The nice thing was it came with an x86 instruction set, but had some extensions to be able to address, for example, larger memory spaces. It also came with an integrated memory controller, which allowed for high bandwidth between the memory and the CPU. The time between 2003 and 2006 went quite well for AMD. They decided to purchase ATI, a graphics card company, because they decided it would be useful to have both capabilities, CPUs and GPUs, in the same design house. Sounds familiar, doesn't it? After 2006, there were some very tough times for AMD, and they almost went bankrupt because of manufacturing issues, which lead to a situation that Global Foundries was spun off as the manufacturing business of former AMD. In 2017, AMD came up with a new concept they called the EPYC processor, and the innovation was to combine a number of chiplets in one large chip module, which was very efficient in improving the yields when manufacturing a lot of CPUs on a single piece of silicon. That went through 4 generations of development, and in 2023, AMD released the Genoa family of EPYC processors, and as we will show you later, it seems like they have caught up quite a bit to Intel's capabilities and now are leading in the performance per price arena.
Okay, so Herbert, I know back around that time that AMD introduced their EPYC line of processors. You had purchased a system with these CPUs, and you made some comparisons with your Intel compute nodes at that time on your HPC cluster. So if you could, please walk us through some of the details on this slide and share some of the conclusions that you made back around 2017 or 2018 timeframe.
Okay, as Jeff said, that slide has some results from 2018, 2019. They were taken with Ansys 19, so that's 5 years ago. And the thing to note is I'm comparing here different CPUs, the AMD EPYC Naples in 7351 and 3 different Intel CPUs from that time. The way I'm measuring performance is with something we call a rating. That is simply measuring how often you could run the same simulation case within 1 day. The higher the rating, the better the performance, apparently. And what you see here is, although from just some fundamental number crunching performance data, it would be expected that the Naples EPYC would be as good as the Skylake from Intel, but apparently this is quite a different performance. And even worse, when you look at the AMD performance on different Ansys versions, you would see that performance would drop between Ansys 16 and Ansys 17 and the following Ansys releases. So it turns out that this is due to some peculiarities of the Intel software or the Intel compiled version of Ansys that checks for CPUs, and at that time for the Ansys 19, or for the Ansys 17. It would just use the latest or the lowest performance enhancements present in this AMD CPU and not what it would actually be capable of. So at that time, the conclusion was it's not performance-wise comparable to what Intel has to offer, and that machine went into the storage without further using for customer projects.
All right, so now fast forward to 2024, and the picture is looking a little bit different than from 6 or 7 years ago. So on this slide, Herbert, you have a comparison between the latest Intel Xeon, codename Sapphire Rapids CPUs, as well as the AMD EPYC and codename Genoa CPUs. So if you could, please share some of the key details that you wanted to highlight regarding this latest generation of hardware from both the Intel and AMD CPU vendors.
Okay, so we basically have two similar sized CPUs. One is the Intel Xeon 8480, comparing it to the AMD EPYC 9474F. The F stands for frequency optimized CPU, and we'll learn later on that the frequency is a very decisive factor in this comparison. Both have a similar number of CPU cores, so 56 cores on each CPU for the Intel version and about 48 cores for the AMD solution. If you look at the clock frequencies, the spread is quite dramatic for the Intel CPU with about a factor of 2. For the AMD, it's a much narrower spread of frequencies that are used depending on how much power is dissipated. The thermal power rating is practically the same, 360 versus 350. They came out at the same time. And the first bigger difference is when you look at the attached memory. So the Intel machine has 8 memory channels, whereas the AMD machine has 12 of those, which leads to a much higher bandwidth. And since the number of cores are comparable, the bandwidth per core is 50% higher for the AMD EPYC machine. On the other hand, they are both supporting the AVX 512 instruction set extensions. AMD has to do 2 cycles to do one instruction, whereas the Intel CPU is faster by just needing a single cycle. However, in the end, it turns out the combination of higher frequency and 2 cycles basically compensates what AMD can do to Intel's performance on the single cycle side. If you look at the prices, it seems that the Intel CPU is substantially more expensive. So these prices are taken from official sources available on the internet. You have something like 10,000 on the Intel side and 7,000 on the AMD side.
All right, thanks, Herbert. So with these hardware details in mind, on this slide, you're showing some key performance results comparing both the Intel Sapphire Rapids processor and the AMD Genoa processor. And so on this slide, we have results from one of your benchmarks where you used all of the CPU cores on 2 of the different servers that you have, one containing a 2-socket Intel Xeon and another server containing a 2-socket AMD EPYC. So
we are again using this rating scale to measure performance, and on the x-axis you have the number of cores employed: 8, 16, 32, 64, and 128. The AMD CPU just has a combined number of cores that's 96. So AMD stops here. For the Intel machine, we have a total of 112. However, if you look at the performance, then it seems that for the lower core counts, the performance is more or less the same. However, the Intel machine levels off beyond the 64 cores, and there's only a very small increase when you go beyond those 64 cores to 100 and 112, which is the maximum that this CPU or this server can provide. On the other hand, the AMD machine increases nicely in performance up to the highest number of cores.
So here is a very interesting slide. It's a very busy slide, but also very interesting and a very telling slide that highlights the hardware improvements that have come over the years and how much those hardware improvements can benefit the typical Ansys Mechanical APDL customer. So in this slide, Herbert, you're now running all of your different benchmark models, which cover a fairly wide variety of simulations involving different geometries, different analysis types, different equation solvers. And you ran each of these models using all of the CPU cores in your two-socket systems with the exact same version of Ansys Mechanical APDL. And therefore now you can demonstrate the amount of speed up for each benchmark from effectively 2017 timeframe all the way up through 2023 using various Intel and AMD processors. So please share some of the key highlights from this slide that you wish for listeners to come away with.
Okay, so as you might have expected from the third slide I showed, the EPYC 7351, that's the Naples EPYC, is the slowest of all the performers. On the other hand, the Genoa EPYC, the 9474, is the fastest for all of the benchmarks. And since you have a log scale here, the difference in performance between those different AMD CPUs is more than a factor of 5. For a time frame of about 6 years, that is quite substantial. You also see that there's been a gradual increase in performance from year to year when you go to the next generation of hardware, so it's always beneficial to use the latest generation that's available. You also see what has been highlighted on the slide before. I'm comparing here two different versions of the Sapphire Rapids, and there's hardly a difference between those two here, although the core count is 64 for this guy here and 112 for this one. So in the end, it seems like what we conclude from this comparison that over the years AMD has quite well in catching up the performance gap, and at the moment we have for single server systems the AMD as a clear winner of this performance comparison.
Okay, Herbert, so on this slide and the next one, these both deal with an issue you uncovered involving the frequencies and power for both of these Intel and AMD processors and what they can actually achieve. Not what's documented by the vendors, but what's actually achievable in practice while running Ansys Mechanical APDL. And this is important detail since the processor frequency directly impacts the speed of all the operations done during the finite element simulation. So if you will, please fill us in on what you
Okay, so just to clarify what you're seeing here is we have used those two different systems on a Linux operating system using a command called CPU power that gives us the per core frequencies currently running. And the measurement has been done during number crunching, so factorization of a matrix, for example. And apparently, there's a big difference in the clock frequencies when you compare the Intel machine with the AMD machine. The AMD machine is able to maintain a clock frequency of around 4 gigahertz, no matter if we are running that with 32 processors in parallel or with 96, whereas the Intel machine clocks down quite a bit from 3.3 to 2.1 gigahertz, mostly because so much heat is dissipated that the clock has to go down to avoid overheating of the CPU. That also manifests itself in the power that is dissipated. I mean, we have the capability to analyze for the dissipated power in the system by just looking at the management interface of the machine, and this gives you actual power numbers for the power supply that provides the energy for the system. And if you look at the numbers here, that's the total wattage of the server. For the Intel machine, it reaches its limits of around a kilowatt already when running on 32 cores, and since it cannot go beyond that for running on 100 cores, the clocks have to go down, and this leads to a decreased performance. On the other hand, for the Genoa system, on 32 cores, it's burning just 650 watts, so apparently it can't go higher to calculate faster, but it maintains the 4 gigahertz clock frequency also when running under full load, and this leads to the performance advantage of the AMD at the higher core counts.
All right, Herbert, thanks for those hardware details, but in terms of the software aspect of running Ansys Mechanical APDL on AMD processors, earlier we had mentioned that Ansys is using the Intel compiler, the Intel math libraries, the Intel MPI libraries, all by default when building and running the Mechanical APDL product. And this was historically true for many years, as Ansys and Intel had and continues to have a very close partnership. However, Ansys also closely collaborates with AMD as well on a number of different efforts. And so starting in 2022 R1, there was a behind the scenes change to automatically use the AMD math library called AOCL, or more specifically, we're using the Bliss library from AMD. And that's used to perform some of the key solver computations. So the Mechanical APDL product automatically recognizes that the user is running on an Intel chip or an AMD chip, and it will either load automatically the Intel MKL library when running on Intel processors, or the AMD Bliss library when the customer is running on AMD processors, so that those solver computations are run in an optimal fashion. And this has been the case now for several years, and it's been working well. And we continue to update both the MKL and Bliss libraries to be the latest and greatest to ensure our customers get the optimal performance on the newest CPU architectures. So further more for that, in 2024 R2, there were some targeted improvements made on the command line parameters that are used when running distributed memory parallel on the non-default OpenMPI software. And those changes are resulting in significant performance improvements as well as robustness improvements for customers who choose to use OpenMPI. And that performance and robustness gains are particularly important when running on servers and clusters that have the latest AMD processors. So another very interesting aspect, Herbert, of these AMD CPUs are this concept of what AMD calls APUs. These APUs are processors that combine both CPU and GPU technologies on a single die. And while APUs have been around for over a decade, they're essentially, in the past, generally for lower end GPU compute levels. But with the recent introduction of the MI300 series of Instinct GPUs, AMD has now introduced a concept of an APU and at a data center level GPU capability. And so, Mechanical APDL has been supporting GPU acceleration and some of their equation solvers for AMD Instinct GPU cards now for several years. But starting in 2024 R1, Mechanical APDL began using a version of the HIP-ROC-M libraries, which is supporting the MI300 series cards. And these MI300 series cards are very new, and there's a lot more testing and benchmarking that needs to be done by Ansys. But the key point I want to make here is that Ansys, again, collaborates very closely with AMD on both their CPU and GPU technology. And we, Ansys, hope to be in a great position to support this new paradigm of APUs that will inevitably help our Ansys customers obtain faster FEA simulation times.
Well, what you see on this inset is basically a combination of CPUs, GPUs, and local memory. It's designed to be used as an artificial intelligence device, so the setup depicted here costs something like $250,000. It should be a simulation guy's dream because it connects CPUs with x86 capabilities, with GPUs and some local high-speed memory with an interconnection that is running basically on the processor bus speed. So that should really give us optimum performance also for simulations. However, the hardware is hard to get because it's basically everything consumed by the artificial intelligence guys, and it will take a while till we get a hand on such a machine to actually measure performance using Ansys Mechanical.
To wrap up today's presentation, Herbert, please summarize some of the key points that you want listeners to take away from today's video.
Okay, so from the data I was showing you, it seems to be obvious that AMD has been able to close the performance gap. This was achieved by an improved memory bandwidth per core and higher clock speeds. So starting in Ansys 2022, Mechanical APDL supports dedicated AMD math libraries, and in version 2024 R2, the Mechanical APDL achieved substantially improved communication while running on a cluster when using OpenMPI. From looking at the prices, AMD is the price performance winner for compute single node, and performance-wise, we observe a tie for running APDL on a cluster.
All right, thank you, Herbert, for sharing some of the things that you've learned over the years in running simulations on your HPC systems and providing some good points for Ansys customers to consider when choosing Intel versus AMD processors for their mechanical FEA simulations.
Well, thanks to the audience for listening and giving us a chance to talk about what happened the last 20 years.
So if you like this video, please let us know, and we'd love to see your comments or feedback. Let us know if you've ever benchmarked Intel or AMD processors and what you'd recommend yourself based on your experience. We'd love to hear any such stories or insights you might have learned along the way.